All right, hello, and welcome to the third video in this group, which are all about us exploring the definition of a derivative, how we might do this, what it represents, all that good stuff. So the first two videos, I think, served as a very good sort of exploration of what is the derivative, what does it represent, and what are some ideas, or at least some concepts, I guess, or guesses really, of how we might actually compute this thing. And that was mostly in the last video that you just watched, was the how do I actually compute or come up with an expression for the derivative, which again, hopefully I've started to impress upon you as a very important concept and literally is what this entire course is all about. So what I wanted to do before kind of moving on with more things is actually just to do kind of a recap video. So this will largely be a review or just sort of re-enhancement, I guess, of the last two videos, the first two videos in this group. But I think it's extremely important to watch this, especially if you aren't 100% clear on what all was presented in the last two videos, which I'll be just totally honest with you. For the most part, you probably shouldn't have gotten it completely unless you've seen this before or, you know, are some sort of a math genius. So because it is a very difficult concept, and but very, very, very important for us to get through. So, and this is the nature of this being an online class and me not actually seeing you all in class, in a regular in-person class. This is typically what I would do, would be to interpret the frowny, confused faces that I would see after a couple days of what you've done in the last couple of videos, and say, okay, class, we need sort of a recap day, sort of what are you supposed to take away from this? What is all this stuff? And so that's what this video is going to be, a good recap. So anyway, so hopefully you've watched those last two, and hopefully got something out of it. Again, the process that we did in the last video especially is what I'm going to mostly talk about today, but hopefully in a sort of better comprehensive and way. Also, this should help you identify, well, what do I need to take away from this? And I'll go right ahead and admit, there isn't, you don't need to have necessarily gotten 100% of everything in this process, but most of it you should. So, all right, so without further ado, this is just sort of a recap. All right, so what did we do last time was on that worksheet, we worked through trying to explore what is the method that you might use in order to find a derivative. And I should say in the first video in this group, we discussed what is a derivative. So I won't sort of go back through that all, but just very briefly, I'll remind you that a derivative is just a function. It's some new thing that we're making up. And what is the derivative? The simplest answer to that question is it's the slope, or it represents the slope. So quite simply, if you have some function f of x, which has some graph and some shape to it and some slopes to it, then what is the derivative? So if I draw you some graph, I'll just make one up here. If this is a graph of some random function, f of x, I'm just making up this graph. Okay, and it might do whatever it does. So I'll just sort of draw a kind of curvy guy, something like that. So, all right, that's whatever. I don't know what the equation of that graph is, but I don't really care. Okay, it's some function. Then what is the whole point of this course, and what is the whole point of the derivative, this new concept we're talking about? So the derivative is supposed to be a new function, but one that is very much based on the original one that you start with, f of x. So here's my picture of f of x that I just made up. And what is the derivative, right? Or what is f prime, as we called it? It should be, so the derivative of f of x, which I'll remind you is denoted with a little sort of tick mark, I guess, or a little apostrophe, I guess, up there. The derivative of f of x, denoted by f prime, we would say that, or f, the derivative of f, is the function whose values are the slopes of f of x. Okay, so it's sort of I guess it's a little bit of a funky concept. It's basically saying, okay, you have some function f of x, and that's what you see on the left here, right? Just some graph of some function f of x that I made up. All right, well, there's lots of things we could say about the graph of f of x over there. Oh, it's curvy, and it kind of goes up, and then it goes down, and then it goes up. We could try to talk about points, I guess, right? I could try to say, oh, what's that point right there, and try to come up with the values or something like that. I guess I could do. So, you know, lots of things that you could say. But one thing that we're focusing on is to talk about the slope of the graph. So, slope is something that I think we have a pretty firm grasp on just from algebra class, that slope, basically it's rise over run, or slope just in general means what is this shape, or what is the direction, I guess is a good word. Direction's a good word. That a graph is heading in, or, you know, just sort of a funny, silly example would be, you know, if you're walking on the graph, and there you are. Sorry if that's not to scale, but you're walking on that graph. The slope is basically a measure of what angle are you proceeding? You know, are you going uphill or downhill? Are you going at a very steep rate, which kind of my guy right there looks like he's going uphill as he's going from left to right, and he's also going uphill pretty sharply or pretty steeply. So that would have a very large slope, or the slope would be a very big number. Whereas by the time my guy gets maybe up here, you know, he's sort of at a flat point, right? And you can imagine walking, you're kind of at the top of the hill. So you'd say, well, what angle or what slope am I going at? It's kind of flat there. So I might say I have a slope of 0, right? Because there's no rise. There's only run, right? There's no up and down. There's only left and right. Right at that point anyway. You know, and then as he keeps walking, if he's down here, you know, then he's obviously on a down slope, so his slope should be negative because he's going down, and so on and so on and so on. You can keep telling this story. So the concept of slope transcends just lines. I know that slope, probably in algebra class, is synonymous with m in y equals mx plus b, the equation of a line. And that's fine. I mean, that's one instance of slope. But slope exists even on curvy graphs, which I hopefully demonstrated to you in my little picture of the little guys there. There is still an idea that for my first guy over here, there is some slope right there, which kind of represents how steep is that particular spot that he's standing on, versus the slope here, versus the slope here. There should hopefully logically be an answer to all of those questions. What is the slope at each of those 3 points, or really at any point on the graph, right? I can pick any random spot, and maybe I want to know what's the slope there and what's the slope there. So the concept of slope is a reasonable thing to want to talk about even for curvy graphs. Okay, so that's where the derivative comes into play, because if I just have a line, a straight line, the slope is a pretty boring question, because the slope is the same no matter where I am on the line. It's always m. So when I have y equals 3x minus 7, 3 is the slope for the entire line. It doesn't matter if I'm at the beginning, in the middle, at the end, it's always 3. But on a curvy graph, as you can see by my 3 little guys, the slope is very much different. My first guy has a positive slope. My second guy has a pretty flat slope, maybe like 0. And my third guy has a negative slope because he's going downhill. So the slope changes. So I can't just get away with saying, oh, the slope is 5 of this graph, because that would be silly. That would say that the slope is always 5. And you can tell, right, that it's not always 5. If it was, it would be a line. All right, so I needed some way of sort of capturing some concept or some way of kind of representing. Well, so then tell me, so I have to have some mechanism for saying, well, what's the slope then at any point? In other words, if I plugged in whatever x value is right there, and whatever x value might be there, and whatever x value might be right there, is there a way for me to know, or could I represent somehow, what is the slope at any of those points? And that's what the derivative is. Okay, so the derivative, this f prime of x, or this, whatever you want to, however you want to pronounce that, is the function whose values correspond to the slopes of this graph up here, of the graph of f of x. Okay, so if I'm at any x value at all, let me just make up a number right here and say that that's an x value of a, whatever that might be. Then if I go down, in this case I go down to the graph, and that corresponds to a point on the graph right there. So I have some concept of what the slope is there. I could kind of just draw it in, right? That's the slope right there. So what is the role of f prime? Well, whatever I think the slope is right here, at the point x equals a, right? If that's a, whatever that number is, then if I go to the graph and I try to sort of draw my little line guy in here to say, well, that's the slope of the graph at x equals a, then whatever number that would be, whatever slope that is, that's f prime of a. Okay? So the slope of that little line I just drew is the value of the derivative at x equals a. Okay? So if I, just to make up a number here, if I computed that the slope there was 2, if I said that little line I just drew has a slope of 2, then f prime of a would be 2. Okay? So the derivative evaluated at any x value is some number. Okay, and what does that number represent? That number represents the slope of the original graph, right? This is a picture that I've drawn 10 minutes ago, is a graph of f of x. So what is this number, which I just made up 2 as the answer, but let's use that anyway. If I say that the derivative, when you plug in x equals a, is 2, that means that in the original graph, which I'm looking at right now, the slope of the graph at x equals a, which is this dot right here, this point right here, that must have a slope of 2. Okay? So the derivative is telling you, what the derivative is going to tell us, it will be the slopes of the graph of f of x at any point that you might be interested in. And what we did in exploration of last time was a way of computing the derivative at a single point, like for example that x equals a point. And what we finished, I think, the last video with was an attempt to generalize that so that I could make a formula. And I'm going to go back through and do that again for you in a few minutes. But while I've got a graph up here, let me do one more example sort of this relationship. So let me try to clear some of this stuff out here. So I'll leave my little guys on there. Hopefully you have a reasonable understanding now of what the derivative represents. And that's just sort of a made-up term. I mean, I'll be honest, it was born out of a need to have a term to describe slope, but generalized. So there's nothing sort of magical about the derivative. This is literally what I've written here on the right is what it represents. Okay, so one thing I might ask you to do is to say, okay, let's say you have a picture, or I make up a picture of f of x, which is what I did over here. And I say, all right, from this graph alone, now we don't have a formula, right? I don't know that this is x cubed plus 2x squared. Plus, I don't know what I don't know what the equation of this graph is. I just made it up. But we have eyes, and we can see what the graph looks like. And so I think actually just from that, we can at least have a sense of what the graph or the values of the derivative should be in order to kind of, make this definition over here make sense. Okay, so in order to help you better, I think, understand this definition, which is super important, let's do just a little bit of exploration here. So I'm going to write under my graph right here, and I did one of these for you in the last video, but I'm going to do one more here. Let me at least give you a sense of, well, okay, if I'm just doing a basic analysis of the slopes of this graph here, I can say some pretty basic things that aren't too hard to see. So I'm going to do this sort of quickly here. But I believe we sort of have some zones, I guess, here where I might say, well, it kind of looks like at that point where that one guy was, it looks like the graph that the slope is 0 there. So I might sort of just denote that and say, if I'm trying to make a little picture down here below of what are the slopes of f of x, I'm going to just try to make a little chart here. And this doesn't require a whole lot of science, really. I'm just looking at the graph and basically trying to identify 3 things. Where is the slope positive? In other words, where is the graph uphill? Where is the graph downhill? That would be the slope being negative. And where is the graph flat? That would be where the slope is 0. And those are pretty easy to pick off. I already picked off the one point where it's 0, and I think somewhere around, I don't know, around here or so, right, is another point where the slope is 0, because it looks like it's pretty flat there. In that case, you're sort of at a little valley, I guess. You're in the bottom of a valley. Okay, and then in between these flat points, I think the slope is either always uphill or always downhill. And again, you can see this hopefully from the graph, that on the left, the slope is always positive. So I'll sort of put a plus sign over here to say the slope is positive over here. In between, that's when the slope looks to be negative to me. That's downhill. And then after this, the slope returns to being positive again because it goes back uphill. Okay, so I don't think it's rocket science to do a very simple analysis and say, well, if I just look at this picture, the slopes of the graph, I can pretty easily categorize them as either positive, negative, or 0. And that's all I did right here. And I made a little chart below the graph in order to kind of represent that. Okay, so what is the relationship then between this and the derivative? Well, again, I'll say it 13,000 more times before the end of the semester. The derivative is the function whose values are the slopes of f of x. In other words, if I want to know what value a derivative has at some x value, the answer to that question is, we'll look at the original graph, find that point, find that x value, and figure out what the slope is at that point. That's the answer. Well, I kind of did that already. I mean, I know I haven't come up with precise values down here in my little chart, but I have at least categorized the slopes as either positive or negative or 0. And since I don't actually have, I could bust out like a ruler or some sort of thing to try to, calculate this, I guess, more precisely. But this is good enough just to at least give us a sense of what the slopes are, right? It's not precise, but that's fine. So what is the tie-in, or what is the relationship? Well, the derivative, the values, or you could say here, if you don't like that, you could say the y values, if you're thinking about a graph. The y values of the derivative are the slopes of f of x, which means if I'm going to now try to draw a picture. Okay, so, sorry, I'm going to come off to the side here and just say this is a picture of the graph of the derivative, f prime. Okay, so that's what I'm going to draw down here in the corner. How do I do that? Well, the graph of the derivative. Okay, so in order to graph anything, we need to know points. Well, what do I know about points? Well, okay, for whatever x value I'm at, let's say I'm just going to pick a random x value right there. In order to know where to put a dot, where do I put a dot? Do I put a dot here? Do I put a dot here? Do I put a dot there? I don't know, right? I have to know something more about what does the function actually, entail. Well, at any x value, I know that the y value, right here, of the derivative, which is what I'm trying to graph right now, is the slope of the original. Oh, okay. So when I'm at this x value right here, I would move up to the original graph to the corresponding x value, which maybe is somewhere around there. And I'd want to know, oh, okay, so if I knew what the slope was right there, that is the y value that I'm going to put a dot for down here in the graph of the derivative. Okay, so I know it's a little bit confusing, but again, the idea is that the slopes up here become y values. And by y values, I mean, am I up here or am I down here or somewhere in between? I don't know. And we don't know exactly where we are, right? This is all just sort of sketching. But we should at least have some sense of a general idea of where I should be. And what do I mean by that? Well, look what I did here in this box. I know that probably seemed like a strange thing to do 5 minutes ago, but this box here was just sort of our summary of what do the slopes of f look like. Well, they look like they're positive, and then there's 0, and then it's negative, and then it's 0, and then it's positive again. So down here, as long as my graph of f prime, or of the derivative, as long as the y values are positive, 0, negative, 0, positive, it's a perfectly acceptable graph then of the derivative. Because again, I can't say this enough times, the slopes of f of x are the same as the y values of the derivative. Okay? They are literally the same. That is the definition of the derivative. So this little chart here serves two purposes. It's a chart, or it's an analysis or summary of the slope of f of x. But it's also a slope, it's also a chart of the y values of the derivative. So if I'm trying to graph the derivative, which I am, then this little chart here is just a chart of what should the y values be, roughly. Well, so the y values should be positive, and then it should be 0, and then negative, and then 0, and then positive. So if I come down here, well, what does it mean to say you have a positive y value? It just means you're up here somewhere. To say you have a negative y value means you're somewhere down here. And to say your y value is 0 means you're on the x-axis. Right? That's where the y value is 0, is right on the line there. So as long as I draw a graph that lines up with the graph above and lines up with the slopes, I'm good. So I'm going to do it now, right? So down here I'm saying I need y values that are positive, then 0, then negative, then 0, then positive. The zeros are the easiest ones to put on first, so maybe I'll do that first. So this 0 right here means the slope is 0. We said our little guy up here is flat. So the slope is 0, but that also means that down in my picture of the derivative, I must have a y value of 0. A y value of 0 means I'm on the x-axis. Okay, and similarly this guy over here, when the slope is 0, which again happens right here, that corresponds to having a y value of 0 on the derivative graph. So those two dots I know are on my graph down here. Now filling in the rest of it there is no exact way to do this, so but all I need to now make sure is that over here to the left, my y values just have to be positive. In other words, I have to be above the x-axis. In here, they have to be negative, so it means I have to be below the x-axis. And over here, they have to be positive again, so I got to be up here. So any graph that you want to draw that has positive values followed by negative followed by positive is okay. And just to make myself not a totally weird person, I might just sort of draw a basic parabola sort of thing, where I'd say, okay, this graph now exactly fits the description of my little chart here. It has positive y values, a 0 y value, negative y values, these are down below the x-axis, a 0 y value, and positive y values. So let me erase my last little things here. But so I think we've done a perfectly good job of coming up with a graph. This is not going to be exact, and I don't care if you drew one that's a little bit different, that's fine. But this is a picture, at least a sketch of what the graph of the derivative might look like. Okay, and you can go in reverse, right? I could give you this graph, right, and say here on the left is a graph of the derivative. I could give you that one, and then say, okay, could you then draw me a sketch of f of x? And it's the same process, just sort of in reverse. So, okay, so that's a little bit more about kind of what the derivative represents, which is slope, and sort of visually, here's how you might try to tie that together, or graphically, I should say. Okay, that was sort of I think what you should have hopefully extracted from the exploration of the derivative as a concept. So, the second thing I wanted to do is spend a little more time recapping sort of our crazy strategy for how we would actually compute the derivative. And I promise I won't take you down that whole path again. I'm just going to sort of cut to the chase. But I wanted just to sort of recap what it is we're doing. I know at the end of the last video, it's a little bit of a magic moment where it's like, oh, okay, all of a sudden we just get this answer. So I want to make sure that that's a little bit clearer for everybody. So how to compute, right? So to calculate the derivative. Okay, so what did we do together in the video? The previous video was we said, well, if you have a function and you have a graph and you want to know the slope, right? That's what the derivative is. Then in order to figure out the slope, I sort of said, well, all right, wherever I am, I'll just draw a made-up graph again here. Okay, so whatever function I have here, this is the graph of f of x. If I want to know the slope at a given point, we don't really know a whole lot about slope. The only thing we could say for sure is slope is the slope between 2 points. That's something we know how to do. If you give me 2 points, we're experts at computing m, right? The slope between 2 points. So in order to try to figure out the slope of a graph at any point, or even at a specific point, sorry, let me give myself a different shape here. Okay, that's better. In order to know what the slope is, let's say, I don't know, right there, at that random point, I need a second point. And our whole method from the last video was that we could pick any point to be the second point. But in reality, wherever I pick, right, if I pick some other point on the line and use that, okay, I could do that. But we were sort of seeing, I think, that some of the guesses I was making were not very good. So, but in general, what is it that I'm doing? If I take a random x value, whatever that value is, then if I want to do slope, I want to figure out the slope between 2 points. Well, I have 1 point. It's right there. That's x comma f of x. Okay, and that's the point in question. That's the one that's sort of my generic point. And my goal is to figure out the slope at that point. Well, okay, I know 1 point. There it is. And again, x is any number. So x could be 4, for example, in which case that point up there on the graph would be 4 comma f of 4, which is just what do you get when you plug 4 in for x into your equation. Okay, that's 1 point. Well, I needed a second point. And we sort of did some guessing, I guess, right? And I said, all right, well, if I pick a second point, I don't know, it's this point, it's this x value. I don't know, I think I tried something like +1. And so I came up to the graph and I said, okay, that's x plus 1 comma f of x plus 1. And then I used that as my second point and I figured out the slope between these 2 points. But we started to sort of say, well, okay, that's all right, but it's not a great guess because I'm kind of neglecting the piece that's between them, right? And I'm not sort of capturing what's happening between them. I'm just sort of squaring it off and saying, okay, what's the line between these 2 points? And it's not a totally accurate representation of what's happening at this point. So we sort of came back with a second guess and said, all right, what if I got a little bit closer? Instead of doing +1, I think I did a half. And he said, all right, so here I am now, and that's some other point, x plus a half, comma, f of x plus a half. Okay, and we did the little estimate here of what's the slope between these 2 points, and said, okay, that's probably better, but maybe still not perfect. So the moral of the story, I'm going to stop drawing because I'm running out of space here, but the point of the story, I think, was that when I do these guesses, which are just slopes, right? This is just the y, y2 minus y1 over x2 minus x1. So each of these is just a very simple computation. What's happening each time when I do this is that my guesses, I think it was believable, were getting better and better and better. And how is it that they were getting better and better? What was making them better? Well, as I move closer and closer to the x value in question, in other words, as I don't move as far away is another way of saying that, right? This here, let me draw that in, right? that was me being 1 unit away. This second guess was me being a half of a unit away. And I think I even did one more, which was like 0.1 units away, but I can't squeeze that in my picture, but you know what I mean, it's right there. So the idea, I think, was that these estimates we were making each time, which I should, let me remind you of what they were, right? When I did my first computation, I think what we did when we did our estimates of what the slope should be, for the first guess, we did, okay, I did the difference of the y values over the difference of the x values. That was for the first, that was the first point, and we're always using this this generic x value as our second point. So that's just the regular old y2 minus y1 over x2 minus x1. Right? That's just what I wrote there. Okay? And of course, the only thing I'll simplify in this is that it's a little bit silly to write the bottom this way. You have x plus 1 minus x. So that's just really 1, right, on the bottom here. So we ended up with something that looked like this. Okay, so that was our first guess that we did. Our second guess, as I already drew in the picture here, was using a half. Was using the x plus a half. So I said, all right, so we did the same computation we did, but now instead of 1 unit away, we were half a unit away. And we computed this. And then we make a similar substitution where we say, okay, it's kind of silly to write that on the bottom there. I should probably just do a half. Okay, and then I think we did one more, which I won't draw it on our picture here, but I'll just remind us that I think we did 0.1 as our last guess. And we did x plus 0.1 minus x. And again, to simplify that, that's x plus 0.1 f of x over 0.1. Okay, and we did these computations with real numbers over here. I won't repeat them all for you, but I think what we ended up with was, I think 3 was our guess for the first slope, and then I think 2.5, and then 2.1. And visually, I think what we saw, hopefully, was that as I moved closer and closer, in other words, as this number here, right, as these little sort of move over numbers became smaller and smaller, my guesses were getting better and better. And so what I think I was really doing each time is I was basically doing just a simple computation over here on the right. Okay, that's what I was doing each time. And our belief, I think, just by sort of looking at the graph, was that these estimates here get better and better as I move closer and closer. Well, what does closer and closer means? Hopefully you can kind of see it. Let me switch to a different color here. So in the first guess, I moved 1 unit away, and that appeared here and here. That was x plus 1. In my second guess, I was a half a unit away, and that appeared here and here. And in my third guess, I was 0.1 units away, and that appeared here and here. So to generalize this then, I'm going to come over here and say, so where is this all heading? I think the idea then is that what is each of these little computations on the right? In general then, what is it that we're computing each time? We're doing f of x plus some number, which I'm going to call h, minus f of x over h. That's what each of these guys on the right here is. Each of these 3 computations on the right is just this, what I just wrote in blue down here, or whatever color that is, but with just a different h value. So what is h, right? H is how far do I move to the right of x. So in my first guess, h is 1. In my second guess, h is a half. In my third guess, h is 0.1. So what is it I was really doing every time was this. I did this for h equals 1, a half, and 0.1. That's what these 3 computations on the right here were. And what did we just say? We said that this guess gets better and better when h gets smaller and smaller. Because look what's happening, right? My h's here are getting smaller and smaller, and my guesses were getting better and better. So the conclusion, the big sort of aha like moment of this whole thing, is that if I can compute, or if I can represent this fraction here, and if I can allow h to shrink down to 0, right? 0 is the smallest number we have. Then these guesses coming down the right-hand column here are going to be so good that we can go ahead and call that the answer. Okay, so it's just sort of like this, any sort of a pattern or sequence sort of a thing. You sort of say, well, if you have numbers like 1.9 and then 1.99 and then 1.999 and 1.99999, you know, I mean, in terms of a pattern or a sequence, you might say, well, if you're kind of a smartass, you might say, well, that's never going to exactly be 2 because you're just going to keep adding 9s to the end. Okay, you're technically right about that. But, I mean, when you're at 1 followed by, you know, point and then like a million 9s, I mean, come on, that's 2, right? I mean, 1.999 forever is basically 2, right? There's no difference. So it's the same thing we're doing here, is we're basically saying, all right, if I want these guesses to be infinitely good, right, if I let h shrink all the way down to 0, right, so when h here is shrinking, it's 1, and then it's down to a half, and then down to a tenth. If I just sort of keep marching this way and say, okay, well, eventually h is basically going to be 0, well, that should make this the best guess ever. And that's exactly what the definition of the derivative is. So I'm going to put that on the fresh slide. Switch back to red here. So in light of this sort of exploration that we did, I think what we came up with was hopefully belief that how do I actually compute the derivative? So if I actually wanted to do this, so if we want to use this method that we just spent so much time hopefully understanding and accepting, then how would I actually do the derivative, which should be the answer to the question, where is that sequence going, right? Where are my guesses heading towards? Then the derivative should be computed by doing that computation. I'm just writing the same thing down that I had on the other slide. This f of x plus h minus f of x over h. Okay, that's just what I had on the last slide. So the derivative is computed by doing this, by representing, or by, you know, writing this down, I guess. And letting h go to 0. Or, you know, this is where you sort of, this is a little bit of the magic, I guess, here, right? When I think about a sequence, I have to sort of eventually say to myself, well, what's happening in the long run? Or what's happening as the sequence of numbers, you might say, goes to infinity or goes on forever? Where is it heading? Same idea here. That's what I mean when I say letting h go to 0. What I mean is to say, well, when h is so small that it's practically 0, what is this thing on the left equal to? That's the answer to the question, what's the derivative? Okay? So this is what we have to do in order to compute a derivative, is basically do this. Okay? So to try to break it down, I'm going to break it down into steps for you in just a second. But before I do that, let me just say one more thing. What is this? Again, I know I've just spent the last, hopefully, 20 minutes reminding you of what we did last time, which were all, these were all slopes. And remember, the slope is the derivative. So what is it that we did over here? These were all just y2 minus y1 over x2 minus x1s. Okay, these were just the regular old Algebra 1 definition of what's the slope. The difference of the y's over the difference of the x's, the rise over the run. So each of these was just a dressed up version of that. Look, you know, let me just point to this right here, this guy. That's the second y value, that's the first y value. That's the second x value, that's the first x value. So every time, you know, I know it's sort of a little bit like, where the hell does this come from? It's just that. On the top here, this is a y value. that's a y value. Again, y values are the same thing as f of x, right? So this this over here, this numerator of the fraction is just the difference of the y's. It's y2 minus y1. Now on the bottom, we lose the fact that it's a difference a little bit, right? But remember, where does the bottoms of each of these fractions come from? It does come from doing an x value minus another x value. It's just that it was a little silly to write that every time, right? Because it's x plus 1 minus x. Well, that's just 1. And this is x plus a half minus x. Well, that's just a half, right? So on the bottom here, technically, well, it's just h, right? Again, h was how much do we move away from x. This is technically, I mean, if it made you feel better, you could say it's actually that, if that makes you feel a little bit better, like, oh, okay, I see it now. It's an x value minus another x value. And that's fine, right? But we all agree that hopefully plus x and minus x are really just 0. So I really don't have to write that every time. I could just write h. Okay? So in reality, let me flip back to my summary then, right? This really is, this guy, this fraction, this magical guy right here, really is just y2 minus y1 over, and it's a little bit missing here, but it's x2 minus x1, which is just going to simplify to h. And how do I know where's the h again? What is the h in my picture? Or in my, in my picture? The h is how far away from x do I look to find my second point? Okay? So again, just kind of keep reminding yourself, in the guesses that we did last time, we employed an h value of 1 to make our first guess. We went 1 unit away from, I think 2 is what where we were last time, right? We were at an x value of 2, so we came over here to 3. Or maybe 1, I'm sorry, it was 1. We were at an x value of 1, so we came over here to 2. And then we did 1.5, because why? That was an h value of just a half. And then we did 1.1, that was an h value of 0.1. And so on and so on. So as the h values became smaller, that's synonymous with saying you move closer and closer to the x value in question. And again, as we said, our guesses become so good that we can go ahead and say that that is the answer. That is the derivative. That's how you can actually compute this. Okay, so steps. So in order to try to give you a little bit of a sort of step-by-step, how do you actually do this each time? And I'll do a couple of examples in the next video, but just to give you the steps first, how am I going to actually compute this? Or when I say find the derivative using this definition here, what is it that you're actually supposed to do? Well, so there's a few steps that just to sort of get you, on the board, and to get your thoughts organized. What is it that you should actually be doing each time? So here's the definition. It's right there. And if I want to compute the derivative, which is what all these questions are going to say for the next week or so, compute the derivative of blah, blah, blah. What do I need to do? Well, in order to compute the derivative, I need to use this. Okay, and you could think about that as a formula. That's fine. It is. It's basically a formula. So if you wanted to compute something, in maybe a chemistry class or something, and you had a formula and it said put this here and that there and whatnot, I don't know. The first thing you'd probably do would be just to fill in what you know in the formula. Okay, so that's step 1 here too. So if I want to actually compute this derivative, step 1 is to I think fill in the numerator. That's the top of the fraction. So fill in basically these two guys, right? Fill in this guy and this guy. Because what is it that you're going to be doing each time is you're going to have an actual function for f of x. In other words, a formula, right? I'm going to say, compute the derivative of f of x equals 3x squared. So you'll know what f of x is. So filling in what that represents in the numerator there shouldn't be that hard. Now I'll just say, be careful. If you know, for example, let me just make up an example. I'll throw it here in the corner. Let's say we're using f of x equals 3x squared. And I want you to compute the derivative of 3x squared. Well, if that's f of x, then this is a no-brainer, because in my fill-in right here, Well, that's 3x squared because, well, that's what f of x is. So that's easy. Now to do the first piece, though, the f of x plus h, I'm just going to remind you, right, the way to think about that is that when you have something other than just plain old x in there, what is it that you're really actually doing each time? Well, that's playing the role of x. So in my formula, so to speak, right, instead of putting an x there, I'm putting an x plus h there, which means in my sort of result, I guess, I should put an x plus h in everywhere I see an x. Okay, so just be careful when you do that. So step one sounds kind of innocent, and it is, but just be careful when you fill in the numerator of the fraction. There's nothing to say about the bottom. Why? Because the bottom is just h. So you're just going to sort of leave that alone for now. All right, so fill in the numerator with what are these people, right? What are these things? Okay, now what are you going to be left with, what are you going to be looking at after you do step one is a whole bunch of stuff, to be honest. You're going to have an h on the bottom, and you're going to have some stuff on the top with x's and h's and numbers, and it could be a whole sort of mess of stuff. Okay, so, well, what is our goal? Our goal, remember, as always, is going to be to do that. And what does that again mean? The idea is that I want to say, basically, I want to eventually be able to plug in h equals 0. But why can't I do that right now? Well, if you look at the fraction, right, the fraction, this main guy that I'm working on right now, if you remembered nothing from pre-calc, you hopefully at least remembered that we can't plug in, right? If I tried to plug in h equals 0 right now, that would be saying that that's 0. And I think one of the golden rules that we learned way back when is that you can't have 0 on the bottom of a fraction, or in other words, you can't divide by 0. So it is illegal for me to plug 0 in at the beginning of the problem. That is my goal. My goal to make the magic happen is that I am going to eventually plug in h equals 0, but I can't do it right now, and that's always going to be true. I should say, you're never going to be able to plug 0 in right at the beginning of the problem, because you'll always be, dealing with a divide by 0 situation. Okay, so if I can't do that right now, then I guess I'm kind of SOL, but I won't be, because what is step 2? So step 1, fill in this, and you got a whole bunch of stuff. Step 2, and you'll always be able to do this, is going to be to simplify the numerator and eventually, hopefully, and eventually you should be able to factor out an h. Okay, so simplify is sort of a loaded term, I guess, right? So simplify means basically do some algebra. Okay, simplify could be easy in terms of things like, if you have x squared and negative x squared, well, that adds up to 0, so you can cancel them out. If you have things that maybe need to be FOILed, right, you could do that. You could do just, it's basically just some basic algebra tricks, combining like things, subtracting, whatever. Okay, algebraically simplify the top. And I promise you, if you did it right anyway, that you should eventually, after you do some simplifying and some combining, you should be able to factor out an h on the top. And again, by that I just mean every term on the top should have an h in it. So if you can do that, if you can factor out an h, well, now I think something good might be able to be happening. Because why? If you end up with something that looks like h on the top times some stuff, and that divide by h that was originally part of the problem is still going to be down there, you now can legally cancel those two h's, which just leaves you with stuff. Okay? So step 3 is to cancel the h's on the top and bottom. Not all of them. You may have stuff, as I've so elegantly called it here. Stuff might have h's in it too. That's fine. But the point is that this h and this h, the h that you factored out and the lone h on the bottom, can be canceled now. And if you do that, that becomes, like a fancy 1, right? So you'd only be left with stuff. So cancel the h on top, and I'll say leaving leaving you with just stuff, whatever that is. Aha. Okay, what's amazing, or what's great about stuff, okay, is that, or I should say, what's great about what you're left with is that you no longer have an h in the bottom. You just canceled it. So that means all you're left with is stuff. Well, that's on the top. In other words, there's no fraction anymore. You just have whatever that is. Well, our main concern, or our main, main concern was that I couldn't plug in h equals 0 at the beginning of the problem because it created a divide by 0. But look at what we've done. We've dealt with that by canceling out that h with this h. And so when you're left with just stuff, whatever that stuff might be, you do not have a divide by h. Again, if you did this correctly anyway, you won't have a divide by h staring you in the face. You'll just have some stuff. And by stuff, I mean x's and h's and numbers and stuff like that. So the last step is going to be your favorite step, which is to say, since you've canceled the h that's on the bottom, you can now plug in h equals 0. Legally, you can do that now. And the result is the derivative. Okay, so what is that, 4 steps or so, I guess? These 4 steps should, will always work. Now, simplify is sort of a loaded term because that might mean a variety of different things. But that's really the only piece where, you have to do a little bit of thinking, I guess. The rest of it's all pretty robotic. And again, just be careful with the fill in. Fill in is shouldn't be a loaded term, but again, having taught this course many times, I sometimes get very creative answers for what happens when you fill in stuff. So, so sort of take your time with step 1, use your smarts for step 2, be careful, I guess, with step 3, and then really step 4 is pretty easy. You're just going to plug in h equals 0, and some stuff's going to cancel out, and the stuff you're left with, that's the answer. Okay? So, all right, so that's a summary, I think, of the first 2 videos. Apologies that this video is almost as long as the both of them, but again, I have to say, you do sort of need to probably hear this all 1 or 2 times, and in this case, you now have been able to hear it twice all the way through. And so what I'm going to do in the next video is will just be a series of examples of computing derivatives this way using this formula here. And that should hopefully help drive home, what it is that you might have to do each time. So, all right, so stay tuned for the next video, which should be posted as well.